Okay, the first speaker in this session is Rob Thu. He's from GAP, Group of Applied Physics, Geneva, well known as the home of quantum key distribution, quantum cryptography, and the place where the first commercial success in this field came from Avadi Quantique. Rob's been there several years developing various new QKD technologies, and he's going to give us an update on quantum communication technologies and ideas in his talk.
Okay, that wasn't me.
Make a big splash.
Indeed. Okay, so thank you, John. And thank you to the organizers for the invitation to this wonderful event. Been really enjoying it. So I seem to have managed to have got a title that's both ambiguous and pretentious at the same time. So hopefully the rest of the talk will go much better than that. So indeed, I'm in a group of applied physics, or department even of applied physics. So I have an applied physics hat, but I work on quantum technologies and teleportation and things like this. So it's a very interesting applied physics group. And why technologies and ideas? I think this sort of reflects a little bit what we've heard over the last day or so. And actually, my talk has changed a bit since arriving. So I won't talk so much on technologies. We use technologies, but why? And I think the driving force between why we develop new technologies and how we adapt these and what we want to do with them depends a lot on the ideas. And so I want to focus a little bit on the ideas that come about and how we come to these ideas. And as John mentioned about commercializing QKD, how we look at this technology transfer process from doing fundamental experiments with teleportation to putting something in a box and selling it. So, very timely. So, in the beginning we had this, I love this picture, this was the first QKD experiments, yes, 30 centimeters, built by theorists. So, it was really the beginning. But if you look at the date, that was 92. And then within a few years, people had worked out how to put this into optical fibers and send it through a communication network and perform QKD over 23 kilometers. So very rapid progress, but it also highlighted certain problems with dealing with polarization in fiber and these sorts of things. So a bit of thought went into that, and a new protocol, a new idea was developed to deal with communication in fiber optics. And you can already see the applied aspect coming out. We've put this in a box, so it's almost ready for sale. But it was not far off. I mean, only a few years later, and with the development of electrically cooled detectors that allowed this to really become a commercial product. And, we know the story of Avadi Quantique. So that's sort of a bit the background of how fast things can progress and why they progress. You meet natural problems and you find solutions, you find new ideas to deal with them. And so today, we're still an applied group. We still put things in boxes. The boxes are smaller, they're prettier, and inside they're actually doing a lot more. I mean, we have systems, we use a lot of telecommunication components as much as we can, but on board we've got a lot of hardware, software. We have FPGAs really controlling all the synchronization, the sifting, all the processing, so that this is basically a turnkey device. You put it in the system and it works. It's all WDM multiplex, so we can deal with the classical communication, the quantum communication, everything in a box, signed, sealed, and forgotten. And this is academic prototypes, and these work very well. This is what you normally spit out. This is around a kilobit of secure key rate over 70 hours, in case you can't read the labeling here. So you see this is a system that's very stable, has a very low Q error of less than a few percent. And what's nice about this, compared to the 23 kilometers before, this is over 200 kilometers. So it's a very useful, practical system. We can push that even further by playing around with various parameters, and with this particular system, we pushed it out just past 300 kilometers. Why we were able to do that is because we use a very simple idea for encoding our qubits, for detecting our qubits. We use all these telecom components. We have all this years of experience in developing good, high quality, reliable telecom components that are all the same. If I buy 5 modulators, I know they're all going to be the same within what we need. And importantly for this experiment, we're using electrically cooled detectors again. So a lot of these long distance experiments have used these nice detectors like Siwoo Nam was showing this morning in his rack mounted system, not the invisible rack mount, but the serious rack mounting. Here, this is with electrically cooled detectors. And so this was only like last year we were doing this, but actually if you go into the corner there, you can already buy this system. It's sitting in a box. And they'll try and sell you one, and you can try and go to 308 kilometers or something like this and see if you can beat us. So that's sort of a bit the QKD type scenario that we do a lot of work on. But there are distance limitations, and one of the big challenges now is to go to even longer distances. So to get past this 300 kilometers, it's pretty much as far as we can go with point-to-point communication. And so there have been trials and networks in Europe back in 2008 with a whole bunch of different platforms all working in the one network. Idicontic and Battelle in the US are putting together a 770-kilometer long network. And as some of you may be aware, in China, they're really investing quite heavily, and they have this plan already started to develop a 2,000-kilometer network with huge number of QKD systems and trusted node devices. A trusted node is just a way of linking these point-to-point devices. So that's very nice. We can discuss that maybe in the panel session, how appropriate that is, or how, if we want to do this. But if we really want to go to longer distances, we need to start thinking about entangled systems if we want fully quantum secure communication. And so you'll all be aware of quantum repeaters, and here's an area where there have been a lot of ideas. The first proposal started off with 2-photon entanglement, but this is a plot that shows how far you can communicate and how long it takes you to get a qubit across. And even these numbers are very optimistic. This is a theorist made this plot. And so what you want to take home is everyone knows the DLC-Z scheme. This is the standard reference protocol for quantum repeaters. And you see here that the time taken to distribute a qubit over 800 kilometers is really rather slow. But there are ideas for using multi-mode memories, allow you to speed this up directly so you can gain a factor of 100 or 1,000 depending on how many modes you can put in. There are other protocols based on single photons that also you can scale down. So these are nice, but what's perhaps not so obvious is these are single photon entangled states. They're not 2-photon entangled states. So polarization entanglement is not really here explicitly. The other area that's interesting if we start to talk about entanglement, and Siwoo Nam touched on this again earlier today, is device-independent. I've said QRNG here because it's much easier to study, but we can think about communication as well in this scenario. And again here, we've been looking at, is it better to use polarization entanglement or 2-photon entanglement, or whether this single-photon entanglement, like DLC-Z type schemes, is better? And actually, what this little plot here shows you is the Bell violation as a function of the efficiency of your system. And as we saw this morning, Siwoo Nam was around 75% here. So they're violating, but only just. So that means in terms of a quantum random number generator or your security of your system, you've only got a little bit of security. You've only got a little bit of randomness that you can use. So what's nice is that single photon entanglement, while we need higher efficiency thresholds, we can't, I won't go into details of why they can get down here, but it's basically because of this non-maximally entangled state that Siwoo Nam was talking about. We have to use maximally entangled states for the single photon case. But it scales much, much better. As soon as we start to get above this threshold, we get a significant improvement and can get significantly better violations and hence more randomness out of our system. So I'm going to talk a little bit about this idea of single photon entanglement and why in some scenarios, let's say it's better than 2-photon or could be better than 2-photon entanglement. And I'm going to touch on something that came up a few times in a few people's talks today is, okay, security, trust, depending on whether you're doing QKD or quantum random number generator or just characterizing your system. Do you trust what you're doing? And most of these QKD systems that we've got are very complex, and we know they're provably secure, but you need to make sure that your device and your security proof is a one-to-one mapping. And that is a very hard problem. So the extreme that we saw this morning was to go to this device-independent scenario. So here, we don't care about the source. We don't care about what's happening inside the box. We get Alice and Bob to make some measurements. We get some outputs. We look at the probability, the conditional probabilities, and we can say whether it's secure, whether we can trust this or not. But as we saw this morning, this is very hard. So what we're thinking about is looking for ideas in the middle, in what we call a grey box. So maybe we know that a particular area of our box is prone to problems, or we can rule that out quite easily. What are a simple set of assumptions that we can make and test and have some confidence, real confidence in, and hence get a better level of security, let's say, without the difficulty of going to this full black box Bell type scenarios. And if we think about QKD, we always hear a lot of noise when a QKD system is hacked. This always makes great news. Maybe Edie Kontig don't agree, but we all hear about it. But most of the time, they're attacking the detector system. So here's an obvious regime where we can say, can we just maybe rule out the potential for attacking the detector system? We trust the rest. And so this was a very nice idea called Measurement Device Independent QKD. And why it's nice is, well, I'll explain how it works first. We have, instead of just a single QKD system, Alice and Bob both, in a sense, have their own QKD system. So they both prepare their states, and they send it each to this central, third party who performs a Bell state measurement. And what's nice here is that even the hacker, spy, whatever, can control this source, but they can't influence the shared secret key of Alice and Bob. And how that works, you can see by thinking about entanglement, because what this is a time-reversed entanglement QKD system. So you can imagine this Bell state measurement is basically projecting onto a Bell state. So instead of having a Bell state measurement, I prepare a Bell state and I send it to Alice and Bob. They can make their measurements. This is a one-to-one equivalence, and we know that this should be secure because it doesn't matter if our hacker has the source, we can still extract secret key material. The problem is that it's not very efficient. Because it's a linear optic Bell state measurement, it only works half the time. So we have low rates. It requires 2 photons, 2 detections. It doesn't help the rates either. But more difficulty is these photons have to be identical. They have to interfere. They have to arrive at the same time. There's a lot of synchronization problems involved. So this is quite hard. And just to give you an idea of how slow they are, this is sort of like comparing recent MDI experiment. At 200 kilometers, they've got 0.018 bits per second compared to sort of like a prepare and measure scheme like I showed you previously. It's running at around kilobits. So you see it's not just a little bit slower, it's a significant disadvantage for this scheme, even though it solves a particular problem. So can we find a regime where this works well? We can take the best of both worlds. And we saw that the Bell state measurement between the 2 qubits, this was a good way of removing the potential for attack on the detectors. And we want to get rid of this problem of synchronization. So what we came up with was an idea where if you have Alice's lab, she can define a qubit system. So here we use polarization in this particular case. She sends it to Bob, and Bob also encodes a qubit. So this is a little bit analogous to what we had here. We had Alice encoding a qubit, Bob encoding a qubit, and now we send it to the Bell state measurement, just like here. So we seem to have all the advantages here, but what we now have is also the advantage that we don't have to worry about synchronizing 2 different systems. We have 1 photon encoded now on 2 degrees of freedom. So once we have the qubit here, 2 degrees of freedom, we can make our Bell state. We can now measure all 4 Bell states. I mean, it's linear optics, but we have more degrees of freedom, so we can actually access 4 Bell states. And this extra degree of freedom removes the need for us to do any synchronization. We don't have to worry about matching photons and indistinguishability and things like this. So this is an interesting scenario. We put it into a system, just using the technologies that we developed for other things that were lying around the lab. a nice heralded single photon source. We can prepare qubits. Bob can prepare his spatial mode qubit, and then we can prepare a Bell state measurement. Slightly complicated scheme, but it's fiber optics, and we actually do some time multiplexing here, so we only have to use 2 detectors instead of the 4 in this case. But then we can look at, okay, Alice chooses her qubits, Bob chooses her qubits, and we see that ideally we want to have 50-50-50 chance here, we want to have zeros here. We see very good correlations, and we can extract a Q-bar of just 1.5%. The rates are slow, but this was the proof of principle in the first case. We have a heralded single photon source. This is not the most practical, but with a little bit of work, we can show that you can use this with weak coherent pulses and decoy states, and so you can then plug the whole idea into something that's got a gigahertz clock rate or something like that. So this is quite an interesting approach to dealing with the detection issue. So perhaps one thing we can take away from that is that these concepts from entanglement-based quantum information can help even for these prepare and measure even weak entangled, weak pulse schemes. And something that we all know but sometimes forget is that photons have other degrees of freedom that can perhaps be useful and lead to more efficient protocols. So I've started to talk a little bit about entanglement before, so can we use these ideas to maybe do something to help us characterize and certify entanglement in a more reliable way? And obviously I wouldn't be introducing the topic if I didn't think so. So, I mean, one of the problems with entangled systems is really sort of verifying the entanglement. So typically we have scenarios where you have tomography or an entanglement witness, you make some assumptions about it being a qubit, you really know what your measurement devices are doing. It has the advantage we can detect any entangled state, but we can also have systematic errors, in which case we can overestimate the entanglement. And to go to the other extreme of Bell test, well, they only detect a limited class of entangled states. It is device independent, which is nice, so we shouldn't have any problems. But it is also needs to be loophole free, so we have this problem of detection loss. So we'd like to find a solution sort of, somewhere in between here. And a few years ago, someone was doing something called quantum games. This is what people studying Bell inequalities do in their spare time. They work out games that they can play with these. But the interesting idea that Buscemi had was to say, okay, instead of just making classical, okay, I'm going to make this measurement or this measurement, let's put quantum inputs into this Bell test. And actually with that, we get access to all entangled states. So that's an interesting option, but can we push that a little bit further to get everything we want out of a entanglement witness? And so the theory people in Geneva worked a little bit on this and developed what we call an MDU, a measurement device independent entanglement witness. And so we have some state that we want to test, and then Alice and Bob can both put in their trusted qubits, some ancillary system. And hence, we've weakened things a little bit. We've had to make an assumption. We have to assume that we can trust this qubit. But okay, that's something we've decided we can live with. Problem is, this is a very hard experiment. It's 6 photons. If you want to do it this way, we have to have a heralded single photon source here, let's say, one here, as well as our initial entangled state. More importantly, and the problem we had with the MDU before, was that we have to start interfering 2 different quantum systems. So we have a photon here that needs to be perfectly indistinguishable from this photon and synchronized. So can we use the same games that we did earlier to find a simpler way of witnessing this entanglement? And indeed, that's what we do. So we flip things around a bit. Instead of introducing another photon with a qubit, we encode in an extra degree of freedom. And this returns now to a 2-photon experiment. We're really just testing the system we want to test. So this removes a lot of problems. So just to give you an idea about how that works, we have an entangled photon pair source. It's an interesting source, but I'm not going to tell this audience about it, but it generates basically HV minus VH states, plus or minus if you like. We have our linear optic circuit. So here we have a system where we can either choose, we have automated shutters, so we can choose whether we just encode 0 or 1, or a superposition, and we can vary the phase, so we have access to all of the qubits that we want. But this is for testing a maximally entangled state, and I said I want to test all entangled states. And so a good way to do that is to probe with a Werner state. So this is just a mixture of the entangled state we're interested in with some white noise. And to do that, I think we're the first ones to do this. I don't think anyone's ever bothered actually generating a Werner state before, but what we did, we introduced a pulsed laser into this system, and we scrambled the polarization in each arm independently so that we can just vary the pulse rate or the intensity of this laser and introduce white noise to the degree we want. And so then we get a witness of entanglement. This is an inequality, if you like. So we again look at these probabilities. If I put in my quantum inputs, tau x, tau y, and I get the answers A, B, you go, am I entangled or not? And what we find is that, yes, indeed, for the maximally entangled state, we're well below this threshold. And as we increase the white noise, we finally get to a regime around 0.4 where we no longer are able to witness the entanglement. I mean, we should be able to, in principle, see it down to 1/3, but you know, I'll just say experimental imperfections, but they're imperfections that don't allow us to see this, but we know that we have a reliable witness for what we do see. So I touched on this a little bit earlier, now that we're talking about entanglement. 2 photons good, 1 photon bad, or 1 photon good, 2 photons not so good. We've been doing a lot of work with what's called single photon entanglement. It has lots of names, even some doubters. It's very simple. It's a single photon on a beam splitter. It really doesn't get any simpler than this. But the problem, if I want to think about communication, is how do I detect this? How do I witness entanglement? And so typically what we do in the lab, we just basically close the 2 arms. We have a little interferometer. We can look at the coherence and we can make some arguments to say, okay, well, the state was entangled. So can we get to a scenario where we can really do this? We can distribute this entanglement and say something about it in the end without having to do silly things. And so we have limited options. The detector systems normally don't work. Photon counting, homodyning. I don't want to do homodyning. So I'm looking at something in between. And this is an idea that's been around for a while, back in the 90s. And the idea is that you take this entanglement and you introduce a weak displacement into the system. So a very weak local oscillator, but you still use the single photon counting detectors. And so, I mean, there was a proof of principle experiment back in 2004, and as far as I know, there were any people silly enough to try until now. And so we have better technology than they did then. You know, we've been working very hard on these sources, detectors, transmissions, all these, you know, tedious technological engineering problems. So let's see if we can get it to work. So we have very nice single photon, heralded single photon sources. But we don't have local oscillators normally. So we had to think about this a little bit because, as you'll notice, we're quite highly non-degenerate here. So we can't just do the standard homodyne detection trick and pick off the pump laser. So some people understand how this works really obviously. Others, it's not so obvious, but we can discuss that for those that are confused. So we're using the same process. So this, normally, if I just pump, will be the same process as here. But now I seed it with a CW laser. This is a very narrow line width laser. And what it does, it stimulates around the pump just photons that should be perfectly matched to this photon. If this filter and this laser have the same central bandwidth, this photon and this photon should also be matched. So we can come back to that if there are questions, but I don't want to dwell too much on that. I want to just make sure that they're identical. So, you know, if we want to compare 2 things, we just bang them on a beam splitter and we look at a Hohmann-Mandel dip. And what we see here is, you know, a couple of curves for different intensities for our local oscillator. And so all these lines take into account is the statistics of the sources. We know that we'll never get a perfect dip visibility with this because this is, you know, in principle, a coherent state and a single photon. But we know the statistics, and what we see is they match perfectly in the experiment. So in terms of what I'm interested in, the indistinguishability of these 2 sources, they're very good. So now I can think about it. Okay, I've got my entangled state. I can introduce a local oscillator and start to do my experiment. The local oscillator's moved a little bit here because what I want is that this local oscillator is a phase reference. So it's going to co-propagate with my entangled state. So if I have fluctuations in my fiber, both the state and my phase reference will undergo the same transformation, and in principle I can guarantee, I can keep the relative phase constant. And then I introduce this displacement and a detector, and just to quickly show you how that works. I mean, a displacement operation we can write like this. If we have a beam splitter with a high transmittivity here, so we come in and most of our state goes through here, and we can interfere this with a little bit of local oscillator here. And as I said, we're coming in the same mode, so our local oscillator and entangled state are just orthogonally polarized. We can just do a little rotation here with a wave plate, hit it on a PBS, performs the same operation, and then we can get it onto a single photon detector. And what that gives us is a measurement operator that looks like this in the 0-1 subspace, so we just keep things simple for the moment. And we see that it depends on the coherent state and on the detection efficiency. And ideally what we want is to have something that looks like a Pauli operator. But what we have is something that's almost a Z operation, depending on the efficiency. And the more complicated one, and the one we really want to access, is the X and Y transformations. And here we get approximately X and Y with a bit of Z. And if we think about this in a space like this is the Z, so depending on the efficiency, we're further up this line. And as I increase my coherent state, I trace out one of these curves. And at some point, I can get down to the plane, and I can then vary the phase, and I can rotate around X and Y. So I have access to this X-Y complementary bases. So what can we do with that? So we saw we were living in this world for quite a while, and we saw that this world is very hard to live in. So can we use this and maybe sort of make a little bit of a jump towards Bell? And so a little bit of a jump in this sort of hierarchy of experiments is something called EPR steering. So I won't go into a lot of details, but basically it's a scenario where, okay, we still don't care about the source. We don't know what Alice is doing. We don't trust this, but we do trust Bob. So it's sort of like semi-device independent. And because such a thing didn't exist for this type of measurement, it exists for other types of entanglement, we had to speak to our theory friends and come up with a way, an inequality of testing this, which I won't go into too much detail for this audience about, but we know we have these measurement operators, and what we want to do is play the following game. We want Bob to ask Alice to perform some measurement X and tell Bob what the answer A is. And if they do that, then we should be able to get Alice preparing a state that's of this form. So it's some state that should be what we call steerable, so on this side of the line, and some part that's unsteerable, so not in this set. So we want to be over here, and so once Bob asks the question, gets his response, he can test his state and again get one of these conditional probabilities, and then we can put that into an inequality and say, okay, if now our steering inequality violates some maximum bound, we can reliably say that the source was entangled and Alice wasn't cheating. So in that sense, it's semi-device independent. So they worked out how we could do this theoretically. They told us we had to be better than 43% efficient. We said, okay, let's try. And this is where it breaks down a little bit, this whole black box scenario, because now you actually want to know what's in the black box. So we have to remove that. And it's just exactly the same as what we have on the other side. The thing is, okay, we don't trust the source, as I said. We don't trust Alice, but this is not going to work if she doesn't do the right measurements. So in principle, she should be doing the same displacement-based detection that we're doing. And so our source, we've been working on this a lot. This is, very proud of this, very nice. High purity, indistinguishability, high coupling. We have very good friends in NIST places that have very nice detectors that they share with us, and we do some nice work together. And because we're telecom people, we do this all in fiber. So now we have a heralded single photon source. So actually, this heralded single photon allows us to sort of claim to a certain extent we have heralded entanglement. All in fiber, we can introduce our local oscillator. We can now do these displacement-based detections. We know what measurements we have to make. And how we will do that is with a fiber-based, polarization-based scheme. So instead of just using a cube and a wave plate, we actually use the birefringence in the fiber. So we can just push on this with the piezo, apply a little bit of pressure. In that way, we can vary the amplitude, and we can vary the phase, And because we're an applied group, we put it in a box so that Eddy Conti can maybe sell it in a couple of weeks, or maybe more. So we know what settings we need to do, and overall we get an efficiency that's around 52%, so we should be good. So we put it in. Bob does his thing, he asks Alice to make different measurements, they vary the phase, and what we see is for basically these probabilities of having no click, a click, or no click, no click. We get these 4 interference curves. The measurement settings we want are these 4 that are indicated by the arrows. We can punch that into our steering inequality, and we find that we actually do violate just 4 sigma if we want to be proud. We can check to see if we're being honest. We can look at the fit, so we have experimental points, but we can also fit the data when we see, again, we still violate, not so much, and the error is a little bit large, but it fits very well with the theory. And I can discuss, this is a little bit high because of this rogue point here, this very critical point here, sits a bit above the line, so our experimental point is a little bit higher, and the error on our fit is not so good. So we're very pleased to see this is the first time, well, the steering inequality didn't exist 6 months ago, and nor did the experiment, so already we've managed to put that all together for a semi-device independent demonstration for single photon entanglement. Just before finishing, obviously there's a lot of people working on this, both in the Quantum Technologies group in Geneva, but the other groups of Nicola Gissin, Nicola Brunner, a few people that did a lot of work on this that have now left to other places. A lot of theory friends and a rogue experimentalist that's given us quite a bit of insight into this 2-photon, 1-photon characterization. And as I said, in terms of detectors, we've had very nice collaboration with NIST JPL for the superconducting detectors used in this steering experiment. So just as a little parenthesis, I want to just put on my political cap and take off my experimentalist cap and just bring to your attention a document that you may have heard of called the Quantum Manifesto. This is part of something we've been working towards for a long time in the community, and probably the number that makes you the most curious is this 1 billion flagship-like scale initiative. Please have a look at it. It's not a perfect document, it's a compromise. It has the input from politicians, from national agencies and scientists, so it's not perfect, but I would encourage you because it is going in a very positive direction. And so, just to recap what we did, I think the technology is very interesting, and I love technology. I love building better technology, but I also want to have a reason for doing that. So I think we shouldn't forget about engineering better ideas. And so we've seen how that can help for QKD technologies. And I tried to convince you that you can do a lot with just 1 photon, whether that's for QKD in itself to avoid hacking, to use different degrees of freedom for entanglement witnesses, or as you've seen in this nice new detection scheme, how we can use that for doing device-independent or semi-device independent scenarios. And maybe if I have 1 minute, maybe? Yes. Okay. There was a question before about device-independent QKD and whether you could do that for quantum, whether you could do that because you have this intrinsic problem of loss in transmission. So there are ideas around based on teleportation called heralded photon amplification, which we've been working on for quite some time. And it's a way of using teleportation to remove noise. So if you have a maximally entangled state here in this teleportation scenario, you teleport the input to the output. But if you play around with this, you can actually bias the state. So if I have a mixture of vacuum and single photon, you can amplify the single photon component, so you can remove the noise. And so this works very nicely. And what you can imagine is that, okay, I put the source on one side, I put one of these heralded photon amplifiers on the other, and any of the loss in between, I can now just remove with this amplification process. And still I have to deal with local losses, and we know how hard that is, but in principle, it's possible. So with that, I'll stop.
Okay.
Thanks.
So the paper's open for questions. Do we have Peter.
On that last slide, you showed Alice having the source of the entanglement, where you basically, so with the teleportation sort of trick, I agree, you can do pretty much anything.
For the teleportation?
Yeah, so literally this one, yeah. And so you can do not only sort of make sure that you have a single photon, but you can, of course, do an actual gate, in which case you have measurement-based quantum computing. And in this case, it's very nice. You do essentially balancing your photon. But was Alice, in this scenario, Alice is trusted? Is that right?
This is my next job. So I trust everyone at the moment. So indeed, in this scenario, we need to look at this. I mean, this comes back to a question about device-independent protocols in general. Do we care about the old physics arguments about non-locality and things like this? Do we want to just care about system efficiency? And certainly, in this scenario, in the short term, that would be my push, is just to worry about system efficiency and see whether we can push that into a regime where we can test this.
Further questions? If not, there's one from Josh.
For this final scheme that you showed, if you require 43% efficiency start to finish, does this prevent you from doing any transmission? I mean, this makes it very difficult, no?
Well, that was for the steering. So 43%, we got 52. We've got a little bit of room to move. If NIST find a better detector, or maybe we're actually building some detectors, maybe we can build better detectors than NIST. That's not going to happen very soon, but we hope. We can push that into the high 90s. But then we're still really at the limit. So what's actually interesting here is that you can go to a scenario where what's nice about this entanglement is it scales to higher multipartite scenarios very easily. This is an experiment we did last year as well with this displacement-based detection. So we did 3-partite entanglement. If I look at my Bell inequality now, probably my threshold for detection is only 67% or something like that, I think, if I'm correct. If I go to 4-partite, I'm getting down towards 50% global efficiency. So if I improve my overall efficiency everywhere and I go to multipartite scenarios, then Bell is maybe more easily attainable in that scenario.
Thank you.
Okay, given that we're running a bit late. Oh, there is a question. A quick question then from George.
Hi. There's quite a lot of effort in making detectors better, and they're already like 90% or above 80%. My question is, QKD will benefit from better detectors. In which sense? Would you rather have higher efficiencies or higher count rates?
I think count rates, but it depends which regime you want to operate. I mean, if we want to go to very, very long distances, high efficiency, low noise is good. We don't care about rates because our photons are never going to get there fast enough to saturate. If I want to talk about metro area networks where I really want to push past megahertz, 10 megahertz, keep going, there, the detector count rate is much more important. And maybe if the efficiency is good, great, but the saturation is more important for the short range QKD. So in all these things, it depends on the scenario you're looking at dealing with. Do you want short distance, fast, or long distance, where you need low noise more importantly than anything?
Okay, thank you.
Okay, so we thank Rob again, and there'll be more chance to ask questions in the discussion.